Okay, so let's start. So, hi everyone, welcome to today's talk. So today we have Andy Yang from Notre. He is a PhD student advised by David Chang, who is also visiting us today. David is also a TTIC joint faculty. So Andy has done a lot of impressive works on understanding what transformer can do and cannot do, and today he is going to tell us about understanding transformers through the lens of formal language theory. Let's welcome.
Yeah, thanks, Junior, for the warm welcome. Thanks everyone for being here. So yeah, today I'll be talking about transformers and understanding them using formal language theory. I just want to start with a historical note. Actually, I don't know if everyone knows this fun fact, but like regular expressions were invented to study neural networks back in 1951 by Kleene. So yeah, this perspective is very old. People have been looking at formal language and neural networks for a long time. Yeah, okay. So yeah, I'll just go through what is going to be discussed today. We're going to look specifically at transformers, and then we're going to find a class of formal languages we call C-RASP. And then we have 3 case studies using C-RASP. We're going to look at the depth, length generalization, and bounds for length generalization using this formal language perspective. And hopefully, at the end of the talk, we'll have a little bit of an idea what kinds of questions and perspectives formal language theory can give us on these more contemporary questions with neural networks. Okay, so if we think about the origin of transformers, back in the ancient times of 2017, they were used to do machine translation. In particular, the setup was maybe different than the typical language modeling setup used today. There's an encoder and decoder part, and usually the task was to take sentences from one language and transduce them into sentences in another language. And if we just start kind of abstracting away the details, we just think of the transformer as some kind of transduction, computing a transduction from strings in one language to another, and very abstractly we can just think of it like this. Transformers as recognizers of strings in the sense that it takes a string as an input and then gives some sequence as an output, and we can consider a string accepted based on the output at the last position, just by custom. So this is kind of the setting we ask. If we can treat transformers as accepting or rejecting strings, then we can ask kind of formally what formal languages they can recognize. And this is kind of a framework that allows us to connect it to a lot of the old work and perspectives from formal language theory. Okay. Yeah, feel free to stop if you have any comments or questions. Yes. And to make these connections is a little not completely trivial, because these classical classes of formal languages that people study seem not to line up perfectly with what transformers behave like in practice. So I put a selection of different classes. We have context-free languages, regular languages, and these called arbitrary languages. They're accepted by partially ordered finite automata, and basically these are automata where once you leave a state, you have to revisit a state. But the main message of this picture is that empirically we don't find that transformers line up with any of these existing classes perfectly. For example, there are say regular language like parity that transformers seem to struggle on, while there are also context-free languages that transformers struggle on, but many context-free languages like DeEC that they seem to perform very well on. So I guess the main idea is this, that existing classical characterizations don't line up perfectly well, so we need some new tools. Yeah.
So when you say struggle on, do you mean like empirically if you try and train a transformer to do it, it's not very good at it? Or do you mean that there's like some pumping lemma argument for like in some extremely long case it theoretically can't do it?
Yeah, in the case of parity, it's been observed empirically that training transformers to learn parity. This parity is like bit string of zeros and ones. Check if they're even number of ones, and there are theoretical reasons why transformers also struggle to learn this.
Wait, that's different. I mean, struggling to learn is trying to represent, because the parity is hard to learn using any model.
Parity is hard to learn using any model. It's representable, but it's also hard to.
But here I think you're saying it's not representative. I mean, in this
Yeah.
diagram, I think the way I should interpret it usually is it's not representable.
Mm-hmm. I guess I'm being informal with the diagram. There are tricks you can use to represent it, but these don't line up very well with how they behave in practice.
But so this should I look at this? Should I understand this diagram as representation or as learnability?
Let's understand it as learnability.
But then are you saying that you can learn all partially ordered finite automata? That seems
Empirically, it looks like that. Partially ordered finite automata is a very, very small class of very simple languages. And I guess there's the recent paper that found an expressive equivalence between transformers and partially ordered finite automata. They could represent all partially
With
ordered
learnability
finite
experiments.
sorry what?
With learnability experiments.
Or okay.
It was a very comprehensive.
But of course, they didn't try all of them.
Yeah, exactly. I mean, it's like a random. You can also learn random automata, right? You can learn automata.
So it's an
I'm not sure.
indication from some experiments. It's not like it's not formally that you can learn it efficiently,
Mm-hmm.
and it's not about expressivity at all.
Mm-hmm.
That's what.
Yes. If I go to someone on the street and what probably someone on the street would consider transformers can do, which is how they roughly behave under training, the message here doesn't perfectly line up with existing classes. Yes. Okay. Cool. Yes. Okay, so we can look at a different formalism for understanding transformers. One popular formalism was this sort of programming language called RASP. It stands for Restricted Access Sequence Programming. And this was a effort to represent transformers computationally in a sort of more intuitive way, distinct from existing characterization. And this was invented by Gail Weiss, and there's also a Python implementation popularized by Sasha Rush. And the idea is you can represent the computation of the transformer by writing these programs that would take functions on keys and queries and then perform some operation when you output the values. So this is an example of a program. It doesn't matter exactly what it says, but the message here is just that there's a way to represent the computation of transformers a little more formally in a way that is distinct from older or existing formal language characterizations. So this is a program that takes a string and reverses it as the transduced output. So yeah, that's just an example. Here we're going to discuss a specific variant of this programming language that we call C-RASP, and then we have some discussions on how to use this to understand transformers. Okay, yes, the main operation we can do in this formalism is count. So we have this counting operation which is read this way. So we can count the number of positions j less than or equal to I, such that p of j, this Boolean predicate, is true. And we'll just go through an example later on to go through the particular definitions. One thing you can do is define this language, the DEEC language, which is the language of all strings of A's and B's. You can think of them as open and closed parentheses, and the string will have matched open and closed parentheses. So, okay, we'll just go through the example. The key idea here is that the program counts the number of A's and B's at each position and has to check that the string has no violations. That is, at no point are there more B's than A's, and at the end it has to be balanced, so they're exactly the same number of A's and B's. And these two conditions define all strings in the DEEC language. Okay, so we can go step through example. Hopefully this gives some intuition on what's the formalism. Okay, so we accept strings, we add a initial beginning of sequence token, and then we have the string here, AAB, ABB, and the program will compute Boolean and integer values at each position of the string. And we step down the string, and the final value at the final position is going to be the output. Yeah, stop me if there are any questions or concerns. So yeah, the first part of the program, we have these initial vectors A and B, and these just test whether the current symbol at the current position is an A or B. So here, the A program line is true at every position where there is an A and false where there's a B, and same for that. The first counting operation counts the number of A's up until the current position. So here there's one A up until the current position, here there's two, this is a B, so it remains at 2, and then it goes to 3 here and there, and so forth. And crucially, these count all the preceding positions, sort of like a causally masked transformer. So we do the same thing with B's. And then the first operation we do that depends on these counts is this violation detection. So this detects if at any point there are more B's than A's. And in this string, it's never true, so this operation is false at every position. Then we can count the number of times a violation happens by performing another count over the B's. And this is 0 everywhere because the string has no violations. Finally, we can check that there are no violations by having another equality check for the count of B's and check this is equal to 0. So the M predicate checks that the string is has matched parentheses, that is that there are no violations. Finally, or second to last, we have this balanced predicate that checks that the number of A's is equal to the number of B's. Is only true at the end of the string here, and at the beginning where there are no A's and no B's. And finally, the last predicate, D, just checks that M and B are true, and these two conditions will define the Deek language of balanced A's and B's. And so this string is accepted because, well, the program accepts it, and it's because the number of A's and B's are balanced at every step. And also notice that the empty string is also accepted because there's a true at the beginning sequence token. Okay. And one characteristic that we care about is the depth of the program. And this depth is just the nesting depth of counting operations. So in this case, the last operation here depends on M depends on C, which C is counting operation, which also depends on another counting operation. So this program is depth 2. Okay. Does that sound fine to everyone? Any questions or concerns?
So how do you count the depth again? Why the program has depth too?
Yeah, so I guess we can define inductively define the depth of every line as the number of counting operations it depends on. So okay, these lines have depth 1 because they're counting. And then V has depth 1 because it depends on depth 1 counting. And then this will be depth 2 because it's counting that depends on counting. And then
So it's the depth of the maximal depth of one of the operations.
okay, cool. So yeah, this kind of just goes into the question of depth. This is one question we can ask is how does depth affect the expressivity of transformers? This is joint work with Mikhail at DePaul and my advisor David at Notre Dame, but he's right here right now. I'll just note that this question of depth has kind of been beaten into the ground from many different perspectives. In particular, there was recent work in the last couple of years investigating lower bounds against transformer depth from communication complexity or MPC perspectives, and why do we need another one of these? In the setting we consider are very parameter uniform transformers, and this level uniformity kind of plays a role later when we discuss length generalization. And also the lower bound technique we use is distinct from theirs, which may be of independent interest. Okay, so yeah, I compiled this a while ago, so it's somewhat out of date, but I just like wanted to notice that, you know, back in the old days, a few years ago, back like for machine translation, people used like depth 6 or depth 8 for machine translation. The original transformer had 8 layers, I believe. And then, you know, people started to realize they could, or people had more budget perhaps, they could make the transformers with greater and greater depths. And I guess after GPT-3, we don't know what OpenAI is using. But simultaneously, you know, people try to see what they can get away with fewer parameters and less depth. So I guess it is, in general, an important question to understand like what depth gives you and what you lose by having more depth. So that's kind of the motivation behind questioning depth. And okay, we investigate this question using the C-RASP model based on a equivalence between C-RASP and transformers under a particular fixed precision assumption. So we define these fixed precision transformers to round to finite precision at the end of every block while allowing infinite precision inside attention. This is a restriction of the expressive power, but later on we suggest that it empirically captures some important properties of transformers. So the result we have at the beginning is that a language L is defined by a C-RASP program of depth k if and only if the language with the beginning sequence token is recognized by fixed precision transformer of depth k. So in particular we have the equivalence, expressive equivalence between transformers of given depths and C-RASP programs of given depths. And what this gives us is just a formal, or maybe a different way to describe the computation of the transformer. And the formality of C-RASP allows us to prove things about it. Cool. Okay. Any questions?
Sorry for the you defined the depth of the program, but how do you define the depth of the transformer?
Oh, sorry. Yeah, number of attention layers is the depth of the transformer. Oh yeah, okay. And then the main theoretical result is we prove a depth separation for C-RASP programs. So we use these languages to separate the left depth level. These are just alternating blocks of A's and B's. Oh, if the syntax here, this just means one or more A's in sequence. So yeah, we proved that LK plus 1 with K plus 1 blocks requires depth K plus 1 to recognize. And yeah, we can prove that K layers is not enough. Yeah, and the technique is different than the other depth results. We use this sort of restriction kind of based lower bound developed by these German people who did some formal language stuff. And it applies to very uniform linear TC0 circuits. And the key thing is about uniformity here, which distinguishes our setting, which restricts our setting and makes the techniques a little bit different. Yeah. Questions? But I'll sketch the proof idea for people who are interested. The warm up here is looking at depth 1 programs. Depth 1 programs are they just depend on the counts of symbols. For instance, the majority just counts the number of A's and ensures there's more A's than B's. And so it's clear to see that depth 1 programs only recognize commutative languages where the order doesn't matter. To handle greater depths, we take deep programs and then reduce the depth until they're depth 1, and then we use this depth 1 idea to prove that something cannot be expressed in a program of depth k by performing this reduction k times. Yeah, okay, I'll sketch the proof idea. The idea is to take this perspective where we plot everything on like a 2D grid or a plane. We can think of strings as paths in the plane. So this string is like B, A, B, 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 A, B, A, B, B, something like that. And each program, depth 1 programs, they define half spaces in the plane. So for example, feat 1 defines this line 2A is less than or equal to 3B. I think it's one of these, yeah. It's V1, I wrote a V1, so it's this one. But yeah, the idea is like where at each position in the string, the half planes it's contained in defines the Boolean values of all the predicates in the program. Okay, so I'm going through this maybe somewhat quickly. And the idea for this restriction is that you can find these regions that don't cross any half plane lines. So this I prime region is completely contained within this intersection of half planes. And the idea is we can fix the prefix and suffix of strings. So any string that has this prefix and this suffix and any path through this subinterval will have constant values over V1 and V2. So the idea is that we can replace V1 and V2, which originally were depth 1 formulas, we can replace them with constants. And this reduces the depth of the program. So now the entire program is depth 1 instead of depth 2, while restricting the strings that are in the language. And this technique allows us to reduce to depth 1 and apply the proof that depth 1 cannot recognize a language in this case. So just graphically, we start with some interval in the plane, we find a subinterval that doesn't cross any lines, we fix the prefix and suffix, we keep doing this, and we keep doing it all the way down until we've reduced the formula to depth 1, and in depth 1, it cannot distinguish the ordering, so we can put any string inside this inner square. So then the number of alternations between blocks of A's and B's, if you remember, that's the language that we had in interest. So we can put as many alternations of A's and B's as we want inside this inner block. So that shows that no program can distinguish between a string with like 10 A and B alternations versus 12. And that's why it cannot recognize, say, LK, which has exactly K alternations. So this is a little quick and hand wavy, but this is the main idea. If there are any questions, I can continue. Yeah. So we try to validate this theory in practice. So we can train transformers to recognize these A-B alternation languages. In this case, we look at L5, which is 5 blocks of A's and B's. The task is to output at every step the next possible tokens. It's sort of the next token prediction task. So at this point, there's 1, 2, 3 blocks, so it can be A or B, and we keep going. And then once there are 5 blocks of A's and B's in the string, we can only predict A or in the string. There can be no more B's. So this is how we check for the transformer being able to recognize the language. So in this setup, we check for different LK, and we train transformers with different depths. So from K between 3 and 12, we train transformers with depths 1 to 10 with a small hyperparameter search. And we train on lengths 101 to 150 and test on lengths up to 300. And there's an off by 2. The results here are off by 2 from the theoretical results above, and that's a little side note due to the setting that we're doing this autoregressive next token prediction task.
So you mean off by 2 because you have beginning of sentence and end of sentence token?
It's a little more. I think it's because in the task we always give it a valid prefix, so it has extra information that's not part of the standard language recognition task. Yeah, I think the detail is not super important right now, but
Okay.
yeah, sorry. But yeah, here's some of the experimental results. Yes, transformers. The dashed line, the staircase line here is the prediction that our theoretical results would make on the transformers in terms of what languages they can express, and these results show a bit about what they behave like when training. So this is testing on some held out set from lengths 101 to 150, it has near 100%. I mean, it has quite high performance on all cases where it has enough depth to express the language theoretically, and then it starts to drop below the line. And if we test on longer and longer strings, the divide becomes even sharper, where once the transformer does not have enough depth to express the language under our fixed precision assumptions, it tends not to learn the language very well. So there's some alignment between our theoretical results and the experiments.
So this is you're training on length 251 to 300 and evaluating.
Sorry. All these graphs are trained on length 101 to 150, and these are evaluating on lengths 251 to 300.
I see. So these are really about generalization, but not. So only the first figure is about expressiveness.
Only the first one is about.
Like purely about expressive. Or maybe
Yeah, only the first one
Even
is.
this graph is also about optimization.
Yeah, but this is not about generalization.
Right.
It's not about like.
Yes, but it's not not length generalization at least. Yes.
Okay. I see. So what kind of like architecture do you use? What kind of like position embedding do you use?
No position embeddings.
Like position.
It would be different if there were position embeddings. Yeah, just standard transformer
Okay,
plug and face with no position embeddings.
So I guess one question would be, did you try doing any like if you use like interpretability things? Can you is it like when you look at the weights, is it obvious like what basic algorithm it's using, or is it just kind of a mess?
I didn't look at the weights, but I would be very curious. Yeah, presumably, I mean, this would have a somewhat simple solution. You just need to like start from position, look back and detect in A or B. So you just need something simple like that. But I would be curious what they actually find in practice. Yes. Okay. So just a summary of this first case study, we have some theoretical results on depth in transformers, and the experiments track the theories somewhat closely. But the theory was about the expressivity, and the experiments are about the learning optimization of the transformer. So yeah. Are there any questions, or I'll move on to the next section.
Maybe one other question, unless I missed it. So do you know what happens if you increase like the parameter count, like basically the width, without increasing the depth?
Yeah, we did I guess at least a modest hyperparameter search while increasing the width. It seems like the width is not the bottleneck in this case, or maybe we didn't increase the width enough. But it seemed that even with some modest search over increasing width, the depth still seems to bottleneck the expressive in this case.
Sorry, I guess related to that though, then is there also with like very small width, is there a different bottlenecking? Like if you made the same plot with width on the vertical axis for I guess very small widths, then I don't know if you would have an idea of what you would expect to see.
Yeah. I think this particular problem is expressible with very, very low width and some number of layers. But I'd imagine you could devise tasks where you could find this width separations.
So I found this incredibly surprising because imagine the following algorithm. Transformer just did the first attention layer to detect if the current token is different from the previous token. And then just like do a summation or counting over all such tokens which are different from the previous token.
Yeah.
Why can't no transformer get the sense like how many operations has happened in the past?
Yeah.
Because this could it become too large or like go beyond the precision?
Maybe it's not the precision. Like yeah, if you could, it just needs to be able to detect the previous position. I would guess it has something to do with the training setup. So
but this is an expressiveness issue, so it's not really.
Yeah, I mean it can express it, but like you can without position encoding to express like checking the previous position.
It's hard.
It's not. It doesn't seem very hard, but it seems to rely on like little numerical things that maybe seem to become difficult.
Oh, I see. So you're saying it's difficult to to check previous position.
Mhm.
In the end, that's something becomes hard.
I think that becomes hard when the strings have very varying lengths. If the strings are all the fixed length, you could just use some constant to check the position, but we can't like have this constant because the string lengths are varying a lot. At least that's my guess.
I see. Makes sense.
Yeah, so that would be interesting. Yeah, I tried some experiments with positional encodings, and like one layer could do a lot of stuff. So it probably is doing the solution that you're saying. It just needs to check for positions where the current token is different from the previous.
Mhm,
You
yeah.
just count them, which is very easy with positional encoding.
Yeah.
Okay, so this kind of segues in a bit to this investigation of length generalization in transformers. This is an investigation, I guess, spearheaded by Michael Hahn, but with a large group of collaborators. And put their names here. So the question here was kind of when can transformers length generalize? And one of the investigations are transformed with arbitrary positional encodings. So yeah, I guess to motivate why this seems to be a non-trivial question. I guess we were talking earlier about this. So if you transformers on the copy task, which is to take a string, and after a particular start copy token, it needs to output exact copy of the string and then end. This task seems simple intuitively. Like I guess highly just need to check for the positions and output the same token at that corresponding position. But the question here is like, if we train on this task up to length n, can we perform well on lengths up to 2n or greater lengths? And it seems empirically, I think this has been observed several times by many people, that it's hard to length generalize on copy using transformers. So I guess this is the results that we had in this paper. We had trained on lengths 1 to 50 and then tested on lengths up to 150. And even if it performs well in the length domain, it seems to always degrade out of domain. And this may seem somewhat mysterious. A slight variation of the task, the unique copy, where all the symbols are unique, has very high length generalization. So finding a satisfying explanation for why one version is possible but the other isn't is, I think, an interesting question. A previous work, I think, that got some attention was this algorithms paper by Hattie Zhou and other collaborators. They posed a conjecture. They conjecture that transformers length generalize on problems with simple programs expressible in this RASP-L language, which I'm not going to define here. So I think the empirical results from their paper tracked very well with this conjecture. However, this RASP-L thing is not a really formal object that we understand very well, and we don't know what can and cannot be expressed in this RASP-L. So the contribution here, turns out that C-RASP is actually quite appropriate for formalizing what RASP-L actually is. In particular, we use a variant of C-RASP with periodic and local positional information. So we have periodic predicates that can test if a position is like even, say, or like 2 mod 5. And we also have local predicates that can test, I guess like Jiren was just mentioning, you can test if like a predicate is true at the predecessor position or like 3 positions behind. So we have these local and periodic testing abilities. Here's some examples of how to use these periodic and local predicates. This is the language AA star, so even number of A's. And essentially you just, there's a bunch of stuff here, but the main thing we can pay attention to is the modular predicate here that checks if the current position is an even. And intuitively this lets you detect whether you have even length string and all symbols are A's. Empirically, transformers with these positional encodings length generalize pretty well on this. And similarly, there's a bunch of text here, but the main message is that this unique copy task is expressible using these periodic and local predicates as well as counting, because the task essentially boils down to just checking the bigrams. Because if the string has all unique symbols, all the bigrams will be unique, and so you can use this to uniquely perform the copy. Okay. maybe this is too much text, but the I guess what we observe is that, yeah, as mentioned before, transformers length generalize well on this unique copy task with relevant positional encodings. The benefit of formalizing RASP-Bell is that we can prove things are not expressible in this C-RASP language. So this copy with repeated symbols is not expressible, and this is I guess it's a communication complexity argument. Like C-RASP can only store log n many bits, while you need more than that to copy the string. There's some kind of a communication bottleneck. Yes, okay. So the main result, which I guess I won't go into due to time, is that if a function is expressible in C-RASP with periodic local, then transformers with positional encodings trained on this idealized training procedure can length generalize given sufficiently long training data. So if trained on strings for some large length, at some point it'll be able to generalize from large n to 2n. And the same applies to C-RASP without positional encodings and transformers without positional encodings. Yes. Any questions about thoughts so far? Otherwise I'll keep going. Okay. Yes.
So can you again explain what idealized training procedure is?
Yes, this is an idealized training procedure that I didn't define here just because it would be very involved. It's like I guess maybe it's in the next slide. I can if this does not seem satisfying, then we can talk again. Yeah. So this is like a idealized training procedure. So given some function, and for each increasing training length, we just pick a transformer, like pick a set of parameters of a transformer that satisfies these three conditions. So this is not gradient descent, it's just some idealized learning setup. So we pick a transformer that has large enough context window that matches all the training examples, and all the work is done by this specific regularizer. We pick a transformer that minimizes, like the parameters have to minimize, they have to have some minimum like norms of different vectors or matrices, and some other terms, which I think are a little involved to get into here. But within this idealized training procedure, where at each step, at each training length, you pick a transformer that fits that training length, that minimizes some quantities, we show that at some point, when n is large enough, the transformer will match the underlying function.
What does match mean? Sorry.
It'll behave the same. It has the same inputs and outputs on the domain.
So for regarding to the technical data, so why do you need? I mean, this is basically what you're doing is just MDL or like right? And so all you need is for there to be like some finite representation. But why do you need the context window? Why can't you just take an infinite context window in your formalization? Do you really need this like finite context window? Why can't you just
Because the setup we were okay. I also elided the details. We were looking at okay. I put in the slide.
This is still with your like finite precision, which allows infinite inside attention and finite outside.
Yes. The setting here was about transformers with these arbitrary positional encodings, and these positional encodings are defined up to a certain context.
Okay, so you're learning the arbitrary positional
encodings. I think if we didn't have the positional encoding, I think this extra machinery was not needed, but this was to handle the issue.
I mean, it's not. I mean, it's a very easy result, right? I mean, you just need to show that there's a finite representation, right? So there's no need for.
Oh yeah. Okay.
So but I'm a bit confused. So if you are learning the positional code, if you're relying on, are you actually relying on the positional coding, or are you just allowing it? Because if you're relying it, presumably all the positional coding past n would be just all zeros. So, are you? I mean, do you really need to use the positional coding?
Do you really need to use the positional coding? What do you mean? Do you need to use?
To get your presentation results, you need positional coding.
These positional encodings are needed. They're needed to express the solutions. I don't know if I'm answering these.
So if they are needed, I'm a bit surprised that it works, because after position n, all the positional coding.
Oh, sorry. Yeah. So yeah, I think the setup is also particular. So So like positional encoding P of I is the positional encoding, and then in training sometimes you add an offset to I. So it'll be able to, it'll see everything.
I see. Okay.
Yeah, it'll see everything within the
I see.
It's going to be a long question, so maybe afterwards. I will ask you after.
Okay, cool. Yeah. Okay, I put a bunch of results up, but the main message is that also it seems that the empirical results somewhat track the theoretical results. In here, I put the green squares are for languages that are expressible in C-RASP, and the red ones that are not expressible. And we can see that length generalization seems to remain high for the expressible languages, and length generalization is low for inexpressible languages, somewhat tracking the theoretical guarantee. And the same is for this class of formal language tasks. I guess the exact definitions maybe are not important. Right? The message is that a somewhat unbiased suite of tests seems to confirm the theory. Okay. So, I don't know if there are any questions. In this section, we kind of formalize this observation that transformers seem to length generalize on some tasks but not others. And this formalism actually gave us a really nice way to express this and tools to show that certain tasks are or are not expressible. Are there any questions? One.
Could you hope that you will always have such an N0? Like maybe you can define, I don't know, it seems to me that for any N0 you could come up with a task such that you will need more length, like you will need a higher N0. Like, do you believe it's true that there exists such an N0?
I think there should exist one. But the question is about, like, is there an algorithm to find the N0? Why should there exist one?
You proved there exists.
Yeah, we have this asymptotic result that in the limit we will eventually we will. So there exists an N0, but we don't know.
No, but there are many other options you don't test, no? Like it's for...
No, but for the number of languages is essentially finite. For each one there's an N0, and hence there's a map. I mean, as long as you limit the
okay.
length of the... For any limit on the
I
length
see.
of the program,
Okay.
there is an N0.
So you do limit, okay.
No, okay, you don't have to limit, but this is the best you can hope, right? You can't hope to have an N0 to work for everything, right?
That's what I mean, yeah, okay.
No, but that you can't hope to, right?
Sure.
Because you can just get languages that always get...
Cool.
For any N0, there's a language that's the same up to N0 but different.
So for every limit there exists such an N0.
For any, but the problem is it's not, the relationship there is not constructive, right? I mean, it's not that you can tell me...
Yeah, I mean, I guess that'll be the next bit. Yeah. So on the bounds, this question is recent work with Pascal, Georg, and Anthony from Kaiserslautern. Yeah, so we just investigated this question of what is N0, is it computable, and in this case, I think we give a negative answer and a positive answer for a restriction. So yeah, we know that training on sufficiently long data lets us length generalize. We don't know how long this data actually has to be. Or there exists a bound, but finding it or giving quantitative bounds on it is the question. So yeah, I think we adopt the framework the formalization of this question by, I guess, Julian and collaborators of non-asymptotic length generalization. So this is just the question of given the class, what is the what is the maximum length string you need to see in order to identify the ground truth? So in the case of all two-state automata, I believe strings of length 2 are sufficient just to separate all the classes into the states. And just checking the time, so maybe run through this a little quickly. So in their work, they showed length complexity bounds. So length complexity is this quantity, how long does the strings need to be in order to identify the ground truth. And for different classes, they showed some length complexity bounds. So they had, they investigated C-RASP of depth 1 and depth 2 with some parameters on the precision and number of heads. and they derived a quadratic length complexity for depth 1, and then a t to the k bound for depth 2. And this is a fragment of the full depth 2 C-RASP. Yes. Also recently, this work showed these bounds for 1 and 2 layer transformers under different assumptions. I think the setup seems a little bit different. So their bounds are in terms of the norms of some quantities in the transformer, and not C-RASP. Yeah. So one observation you make is these previous results concern depth up to 2. So you can wonder why don't we have these bounds for greater depths? And we give a answer to this question in the sense that these bounds are uncomputable for the full C-RASP and full transformers, I suppose. Yeah. Okay. Yeah. Okay. So the key observation we use is that length complexity is computably bounded if and only if language equivalence is decidable. And we show language equivalence is not decidable for C-RASP programs with depth 2 or more, and this applies to transformers with our equivalence as well. Maybe it's a bit technical, but the reduction is from Diophantine equations, and these are just like polynomial equations with some number of variables. And this was Hilbert's 10th problem and shown undecidable by actually a lot of people, but I think the final key was shown by Maciejewicz. I forget which year. But yeah, this is going to be somewhat hand-wavy, but yeah. If we recall the definition of C-RASP, we can natively express these addition constraints in C-RASP, so that the technical thing we need to do is how to encode multiplication. And we encode this using this sort of DEEC-like language. So at the end, any word in this language, so the alphabet is variables x1, x3, so on, and we have these filler tokens y3 and y2 just to make the construction work. So at the end, any word in this language has to satisfy that the number of x1s times the number of x2s equals the number of x3s.
Clarification.
Yeah.
Question. So for x1 times x2 equal to x3, their x1, x2, x3 is not the same as your token of vocabulary, right? These are variable, integer variable.
Oh, sorry. I write these as tokens.
No, but for x1 times x2 equal to x3,
Mhm.
How do you define multiplication over
sorry.
tokens?
I guess or I overloaded the notation.
Okay.
Yeah.
Fine. I'm sorry. Just double check. Yeah, makes sense.
Yeah. Yeah, so okay, yes. And then yeah, so the language is non-empty if and only if the Diophantine equation has a solution, and this was shown undecidable by 1993. Yes. Okay. Sense go through. Yeah. So I think the intuition, the why this works is because we can do this sort of DEEC-like encoding where we can iterate something in the parentheses many times. And so these bounded DEEC-like languages, I think, are the key to simulating these sort of non-trivial loops as opposed to trivial ones like just A star. And I think this relates back to observations made by the authors of the non-asymptotic length generalization paper, which is that their languages could not express these DEEC languages, which I think is one reason that they had the computable bounds. So we can show that their fragment with no constant biases, so all the lines pass through the origin, these inherently cannot express the DEEC languages or anything like that looks like the DEEC languages. Basically, they become imprecise as they go farther and farther away from the origin. And I think this is key to why they can't express the DEEC languages. And these DEEC languages sort of like express the loops, like loops in Turing machines or something. And maybe that's why we can avoid uncomputability. But this is a little bit speculative. Yeah. I'll just close quickly so we have enough time left. So we also identified a subset that has computable length complexity bounds. This fragment of C-RASP also avoids these DEEC languages, and it replaces all the programs so that they only use positive coefficients, and we can only check the counts add up to a threshold. So basically we can count up to a threshold. And in this case we get exponential length complexity bounds by having this restriction. Yes. Okay. Yes, so in summary, we address the question of length complexity and length generalization bounds for C-RASP programs with greater depth and thus transformers. Then we show it's uncomputable in the general case and give an appropriate restriction that attains exponential bounds. So yeah, we went through a number of things and we started from some sort of formalism and we used it to explain some things that we observe in transformers. And okay, I put a bunch of text on this last slide. So about, you know, why, what this formal language perspective gives us. Two things that I think we gain from this are, one, that we get a lot of lower bound techniques from the literature on formal languages because they've been studied in many different ways. So we can use these to on transformers and perhaps neural networks in general that are of a similar setup. And then this perspective also gives us, you know, a library of classes that we understand very well. And we can use these as ways to measure the strength or complexity of the network. So yeah, we use these perspectives in the 3 case studies that we've looked at. So yeah, that's what I have for today. So thanks you all for listening. Let me know if there are any questions or concerns.
I'm curious, I hope it's for the quantitative length generalization results. How did they extend if you have errors like, okay, so think of it this way, if I only have a sample of inputs of length up to length n, then I can learn, let's say it's even like a good like uniform sample or something, I'm not even sure what that means, but I can learn I can find something that has small error on inputs up to length n. How do the results extend in that case to that I can get small error for larger lengths, or once I have even small errors, do these break down?
I don't have a satisfying answer on top of my head. I think presumably like these, the reason it's uncomputable is that there are
No,
these.
I'm talking about the positive one. The
Oh.
results. The negative result is still negative. I mean, that's
Okay.
like,
Okay. Oh, positive results. Okay, I don't have a good intuition how it extends with errors.
Like you first like to quantify what means small portion of error. You don't have probability measure here.
epsilon.
You don't have measure here.
That's true. So suppose it's so as I said, it's a problem, right? But even if it's over uniform, say,
Your uniform is you don't have me.
well, it's strings, right? I have epsilon error over strings of length n. Can I get, you know, small error like, you know, epsilon or like, you know, some function of epsilon, I don't know, g of epsilon error on length of strings 2n. I mean, you're right, the distribution is important, right? Because, I mean, really what I want to ask, if it, maybe when I can ask more, but then you probably get a negative result, that for any distribution over length 2n, if I see just things conditioned on their lengths that are less than n, that's not going to work, right? That I can show you that you can never get a guarantee that that will work. But at least for uniform, maybe.
Yeah. Also, if you just want like error to be epsilon for uniform distribution, a lot of things gets much easier.
Well, yeah, but I mean, it's still harder than this. Here you're getting error 0 for uniform distribution. Like here you require training error 0, or like I think of just training error on the sample, but that really what that gives you is like error 0 on length less than n, and you're guaranteeing length 0 for length 2n, or any length actually. I mean the 2n again I think is just you don't really need that here. I don't know, maybe for the position embeddings, but you can probably get away with that.
Doesn't that depend on the
target functions for you. Because like
Well,
for in the worst case, we can always consider if it's not exact identification, there might exist some target function and very huge error.
well, so these results are for specific target functions, and they say for these target functions, some are not possible, right? So if you make, what these tell us is if you make 0 error on length n, then you're going to make also 0 error on length 2n for some explicit n, right? For 2 to the k, right? But now I'm asking, okay, does that mean that also if you make epsilon error on length n, are you going to make small error on length 2 to the?
Yeah, I'm just suggesting that it might depend on like for
Well,
the
asking
platform.
for these
Yes, for these
specific classes.
Yeah.
I mean,
Okay.
or maybe in general you can say that if you can get a guarantee for for any function class, if you get a guarantee with no errors, you can get a guarantee with small errors.
That this result has anything to do with like how like I mean generalizing to it does it depend on like how the for example there is in practical training we don't necessarily see that after a certain for example there might exist cases where we see that from 2 and hope to generalize to that's 1 2 and then I don't know like how does it depend on how the in domain and the out domain are split.
Split with
I mean, this, like, does it generalize to like? Does this result generalize to other way of like? I mean, the how you split like.
Let me try to. So what you're showing here is an out of distribution generalization for specific training distribution and test distribution. It's really not even test distribution. It's like a training set and test set. So your training set is all strings up to length n, and then you're testing on all strings up to length 2n. But you can think of other types of splits. For example, you have an alphabet of size 10, and you're training on everything that doesn't include 7, and you're testing on things that include 7. Okay, that's another type of split. Right? Or you can think of all kinds of other splits. Okay, and I think Jinshan's question is, can you generalize these results to other splits or to all splits? Or I mean, to all splits, I can already tell you cannot, right? So, but like, I mean, I think.
Let's see. Are there other specific subclasses where it behaves differently?
I mean, for example, what you might hope is if the split is simple, in the sense that if the split itself can be characterized by a simple language. And what were some other characteristics of the split? So the thing is, for any split, maybe so the asymptotic length generalization you can get for any split. It's kind of like any hierarchy of splits. Okay. Because it's really just, I guess the way I see it is an online learning result. But the question is, can you get finite guarantees like you have here for more generally or for other splits?
Splits not based on length. I don't have an answer off the top of my head. It seems these classes are not super complex, so maybe there's some tricks that you can see how it behaves. I don't have a good answer. It seems are we restricted to the threshold counting? If we split on call this here, I'll have to think about it.
Any more questions? Let me ask the last one. So practically, you would not like just rely on whole this length generalization. You would like to have like bunch of short data, just spend some money to find long data to mix into short essay, right? And if that works, it would be great, right? And I think this question here is, do you think these results will change drastically if you just mixing small bits of long data and still want to get accuracy up to certain lengths, but then you have different amount of data up to a certain length, and then you have like small amount of data for this longer lengths.
Oh.
I guess it's like this. It's also related to active learning. You get kind of like a question of like what kind of data you want to get labeled. So, but I guess this is like beyond the current talk. But I guess the question: do you think it's going to change the generalization fundamentally?
I don't know. I feel like it won't. I feel like the landscape, especially as you get deeper and deeper, the landscape gets much more like the complexity just seems to compound, and like a small amount of extra examples doesn't seem to be able to like reach into all the crevices and distinguish everything. I don't have a quantitative, but in my senses it seems things get pretty complex. I don't know if a small amount of extra training examples is helpful, but I don't have a quantitative sense of what it means.
Sounds good. So if no more questions, let's thank the speaker again.